Uh, in this problem, this is a system of differential equations, nonlinear. In this problem, the novelty is the presence of the parameter a. So how do you discuss the equilibrium point and their classifications when you have a parameter a in your system? So this is what the spirit of this problem. So here first let us write the system dx dt equals x minus a dy dt equals x minus y squared. So first let us discuss the equilibrium points of the system. So we have to solve x minus a equals 0 and x minus y squared equals 0. So of course this gives me x equals a and x equals y squared, which implies that x equals a and y squared equals a. So here the conclusion is very quick. Number one, if a is negative, the second equation has no solution, so we have no equilibrium point. Two, if a is equal to 0, so in this case we have one equilibrium point, 0, 0. Next, if a is positive, we have two equilibrium points, a square root of a and a minus square root of a. Okay, so this tells us the existence of equilibrium points vis-a-vis the parameter a. And next we want to classify these equilibrium points, whether they are sinc source, etc. Okay, for that, so the classification of the equilibrium points, we need the Jacobian matrix, which is very easy in this case because the purpose of this problem is not to give a complicated functions, but just to see how you manage the discussion of the whole problem vis-a-vis of a parameter. Okay, so here the derivative of it gives me 1, and then there is no y in the first equation. Second equation gives me 1 again, and minus 2y. So let us look at the case 0, 0 first. So 0, 0. So we have g at 0, 0 equals 1, 1, 0, 0. So the characteristic equation will be lambda squared, the trace 1 plus 0, 1, lambda. And then the determinant will be 1 times 0 minus 1 times 0, 0. So this is lambda squared minus lambda equals 0, which gives lambda equals 1 or lambda equals 0. So since 0 is an equivalue, so we have no conclusion on this point. No conclusion means that the Jacobian technique fails. If you want to have a better discussion of what's going on at 0, 0, you may have to use other techniques like the no-Klein's techniques. So the next equilibrium point is a square root of a. So the coefficient, the Jacobian matrix at this point is gonna be 1, 1, 0, and minus 2 square root of a. So this tells us, okay, so now we need the characteristic equation, lambda squared, and we're gonna find minus, and the trace 1 plus minus 2 square root of a, lambda, and then the determinant minus 2 square root of a minus 0 equals 0. So this gives me lambda squared 1 minus 2 square root of a lambda minus 2 square root of a equal 0. So here, this is an exercise to leave it to the student, this is lambda minus 1 times lambda plus 2 square root of a equals 0, which gives me lambda equal 1 or lambda equals minus 2 square root of a. So as we can see, one eigenvalue is positive and the other one is negative, so we have a saddle point. So this tells me that a square root of a is a saddle point. The last point is a minus square root of a. The Jacobian matrix in this case is 1, 1, 0, 2 square root of a, which gives me lambda squared minus 1 plus 2 square root of a lambda plus 2 square root of a minus 0 equals 0. So being careful about algebra, this is lambda squared minus 1 plus 2 square root of a lambda plus 2 square root of a equal 0, which is, again, using algebra, this is lambda minus 1 times lambda minus 2 square root of a equals 0, which gives me the roots are lambda equals 1 or lambda equals 2 square root of a. So both of them are positive, which tells me that the point a minus square root of a is a source.